I'm Paul Gazzillo. I'm a assistant professor of computer science here at UCF, and I'm going to be talking to you about making highly configurable software reliable and secure. So what do I mean by this? What is highly configurable software? Well, if you're a device manufacturer or you're a system administrator or setting up a data center, it wouldn't be very economical to have to write all the software from scratch every time you build a new device. So what most device manufacturers do is they take a set of existing software, like the Linux kernel, Apache web server, and once they design the kind of device they want, they just take a bunch of existing software and repurpose it to use in their refrigerator or their router, or their mobile device, or their data center. And so this notion of configurability makes software really, really easy to use because it allows these system builders to take an existing piece of software that may not have been designed for their particular device or application, and without having to reprogram it, just tweak a bunch of configuration options to enable and disable features so that the software will automatically produce a new version of that software. And so, for instance, in the Linux kernel, which is a common component of operating systems that's used in billions of devices around the world, it has this hundreds of thousands of lines of code that's just devoted to generating a variation of the kernel software, just given some options that the client of this software can use to customize their software. The problem is that while this is great for reuse, this complicates maintenance. So each one of these variations of the program could have its own flaw, could have a security violation, could have a bug. But the way current practices work is that each of these variations has to be configured separately and tested individually. And because there are just trillions and trillions of possible variations of these programs, something like the Linux kernel has thousands of options that users can choose from to customize their kernel. It's just infeasible to try to test all of this one by one. So in our lab, we've been tackling this problem from a bunch of different angles. And here I've listed out several of the students we have on this project. So a couple of highlights. I have a new student, Brent, who just started this year, and another student who's graduating this year. So his dissertation will be in the summer. So I encourage all to come and look at what they're working on. And so we've been tackling this kind of sub-project in our lab from a bunch of different angles, using a lot of different techniques from computer science. And I'd just like to go over some of the highlights and a few of the kind of recent results we've had from this work. So the first approach that we have been looking at is to see if we can analyze or test all these configurations simultaneously. And this may seem a little crazy at first because there are just so many variations of this. But what we do is we use some existing techniques and newly developed techniques from program translation to automatically take these programs from a form where we have to test them one by one and turn them into a form where we can actually run existing testing and bug finding tools on the entire set of variations simultaneously. And as you can imagine, this is a tough problem for scalability. We need to make sure that our representation is efficient enough to allow these existing testing tools to still work efficiently. And so this is our most recent publication. We had a publication this year in the Maine Software Engineering Conference, and this was done with collaborators at UT Dallas and some of my collaborator students, and also Brent, the first-year student. So he had his first co-authorship in his first year as a PhD student. So congrats to him. One of the second angles we looked at is if you look at how this software is implemented, there may be hundreds of thousands of lines of code that are just devoted to the build system, just to the part that is made to generate these variations of the program. And these configuration and build systems have become so large that they are their own kind of software product in their own right. And so what we looked at is developing techniques for making automatic bug finding and testing for this component of the software. And so we looked at the Linux kernel source code and identified and made a bug finding tool that could find configuration dependency errors. So basically these would lead to broken or invalid builds of the software. And we found that we could automatically find these pretty quickly and found hundreds of these. And we were able to take several dozen of these and report them to developers, make patches, get them committed. And even though these are not super, world-ending bugs, they were reliability issues that the developers cared about, and they committed them into the Linux code base. And so now we've got dozens of these bugs committed, fixed and committed into the code base. And so this, we reached out to the largest test infrastructure for the Linux kernel, which is called it's run by Intel. It's called the Zero-Day Test Robot. And they've shown interest in actually integrating this in their test infrastructure to be able to find these kind of bugs automatically in the future. The most recent work we've been looking at is trying to improve how existing testing tools find the right configuration to use in order to identify bugs. So the main crux of this is that if we could zero in on the right code to check that might have the highest likelihood of having a bug, then we could tell testers and maintainers what configurations to use when generating variations of the program, so that they can just zero in much more quickly than just randomly trying lots of different variations. And so this work is still yet to be published. But what we showed is that given changes in the code, we could automatically zero in and generate the right configuration files for test infrastructure to use, so that it can ensure that any changes that developers make get tested. And so it might be a little surprising, but current practice uses lots of configurations that don't even test changes that are made by developers recently. So this graph just shows that if we take a bunch of existing configurations, most of the time before we apply our magic to improve these configuration files, they just don't even touch the changes that are made by developers. And so we just released our tool that enables, this is also for Linux, that enables Linux maintainers and testers to target changes, recent changes in the code. And we're also talking to Intel about this to integrate this in their test automation so that they can hopefully more quickly find bugs and problems before they end up in the mainline kernel. And so they're currently looking at a proof of concept for this. They'll hopefully get back to us, and we'll have some data on the end of the year to see how well or whether this works in practice, like we saw in our testing. So these are a bunch of individual projects to try to tackle this problem of software reliability for this kind of this kind of configurable, highly configurable software. But this is just one piece of a larger kind of national and worldwide problem. One piece of software may be millions of lines of code and may have trillions of variations. But computing devices are made up of lots and lots of these software components. So this just exponentially grows the complexity of this problem. And this has become a recently recognized issue at the national level with a White House executive order examining a bunch of cybersecurity issues, one of which is software supply chain security. So because device developers and manufacturers repurpose most of the software that they use, making sure that the provenance and safety of this software is sound and works correctly together is an important problem. And so also we're looking at how we can help tackle that problem, and also look at some improvements to language design to help make this software safer to write and easier to test. So that's all I have for today. Thank you so much for your time, and I'm happy to take any questions you may have.